is stochastic price adaptation, waiting list, and stochastic gradient descent. Let me not try to explain this now, but I'll go through, and throughout the talk, I'll tell you how exactly we connect all those different things into hopefully one coherent paper. And this talk is based on work that is joint with Itay Shlagi and Peng Yushain and Amit Saberi. And I should point out that Peng Yu is a student in Colombia who did all the hard work here. So he's amazing. He's on the job market right now, in case anybody is interested. Okay. Okay, so let me start by just telling you the kind of motivation or perspective that we want to take in this paper. So we think of waiting lists as mechanisms that are interesting for two reasons. One is those are mechanisms that are very commonly used. Think of organ allocation or public housing, which is the example that I will mainly kind of use to motivate things today. In a sense, this is a competitive equilibria style allocation system where agents face a choice between different items. For each item, there's some associated cost that it's not quoted in price, it's quoted in waiting time. So for example, if you think of applicants for public housing in New York, you sign up for the waiting list. For a while, nothing happens. But at some point, the Public Housing Authority will ask you to come and report your preferences. And the way they make you report your preferences is that you get called on and they tell you which public housing project do you want to join. There's projects all over the city. Even if you think just about Brooklyn, there's maybe a project in downtown Brooklyn and there's a project that's far away in the Rockaways at the edge of Brooklyn. And of course, some of those projects will be more desirable than others. We need some mechanism to ration who should be going to the more desirable locations, who really cares about being in downtown Brooklyn. And waiting time is often the mechanism that quotes this price. If you want to be in downtown Brooklyn, great, you join on the waiting list for the downtown Brooklyn project, but it will take you 2 years. If you want to join the Rockaways project, you can join their waiting list and only wait in expectation for 6 months. And you can think of this as quoting a price for each one of the objects. Agents see the length of each one of the queues, they see the implied prices for everything, and they have a very simple choice. From the agent's perspective, the choice is very simple. The waiting time is basically prices. And you basically choose your item out of a menu. Is the same as the choice that an agent in competitive equilibria has. Really, that's the simplest kind of choice that you can pose to an agent. One big difference that we're gonna focus on is that in the waiting list, there is some choice with something that looks like prices, but those prices are not given by a designer. They're not dictated from above, they're endogenously learned. So usually when we think of marketplaces, we usually ignore the question of how we discover prices. We have some equilibrium condition and say there's invisible hand or some sort of way that's kind of brushed away that the market kind of clears. In the waiting list, we know exactly how the market cleared and how prices adjust, which makes it a very kind of natural parallel first stage to just think about price adaptation. We know how prices are exactly formed. And it's kind of like a total process. If you have some project that's over-demanded, people join it. As each agent joins it, the price essentially goes up. Every time somebody joins the queue for this project, there's one more project in the queue, one more person in the queue, the waiting time goes a bit up, and you can think of this as a totonomar. Every time somebody takes item J, it's another person in the queue for item J, increase the price a bit for item J, but you'll have to wait behind one more person. So this brings to a key feature of waiting list that we're going to focus on for this talk, of this price discovery, price adaptation. And one important thing to keep in mind is that there's no convergence here. Often we think of prices as being learned once and then we're done with the price discovery, we set the prices forever. But the waiting list actually adapts the prices continuously and adjust them, not like just at the beginning when you need to learn, but continuously adjust them. And prices will always fluctuate a bit because every time somebody joins the queue, like now there's one more person that you have to wait. If it happens to be that when you get called in that week, just 3 apartments in some project became available the week before, suddenly you may face a randomly low expected wait for this project. And there's going to be some randomness and fluctuations. And in a sense, you want this to happen because like the world doesn't necessarily stand still. Maybe the local ways was bad last year, now it became better. In a sense, we don't want to close the system and say those are the prices forever. We don't want something that continuously adapts. But on the other hand, the fact that it continuously adapts means that there's going to be those fluctuations and there's going to be some loss from all those fluctuations. So in order to kind of like just illustrate those fluctuations and loss, let me start from like just talking about a simple one-dimensional example. Okay? So let's think of a simple market. It's going to be dynamic. Things happen over time. There's a single kind of item that arrives as a Poisson process at rate 1. Agents arrive as a Poisson process at double the rate 2. And each agent that arrives has some valuations that run IAD from the uniform interval 0, 1. And agents can either join a queue to wait for this item, or they can leave immediately. If they leave, they get a utility of 0. If they join the queue, they get a quasi-linear utility. They get their value eventually once they get assigned, but they have a waiting cost that's 0.02 times the time they wait. So each arrival costs you 1 in 50 of the maximal possible value of the item. And we can ask, what is going to be the optimal allocation here? What will happen under the skew allocation? And one way to kind of ask what is the optimal is to simplify the problem and say, like, suppose we had a planner that could ignore the arrival process. Suppose instead of like just dealing with the dynamic arrival process, we give some more power to the planner. Whenever some item arrives or when some agent arrives, they're frozen in time. We accumulate until some large time t. And then at time t, we unfreeze all the agents and items that arrived and then just make a big batch assignment, a one-shot assignment for everybody. So under this freezing and unfreezing, of course, we should be doing better, right? That kind of relieves the kind of the dynamic constraints on how agents arrive. And in that case, like the problem becomes very simple and then basically the same as assigning things in a competitive equilibrium in a regular market. We can assign half the agents because we have twice as many agents arriving as we have items. So if we bash everybody together, half the agents will get assigned. And of course, the optimal thing will be to assign the agents with a high value, like the half of the agents with the highest values. Yeah. And we can think of the dynamic assignment as something that should aspire to get to the same kind of efficiency. We would want to see whether we can actually get the dynamic allocation, or we do get the dynamic allocation under a simple queue mechanism that actually assigns the agents with value above a half. Yeah. Well, because it's a very simple example, I can just calculate what is the distribution of queue length under the stationary system. So suppose we run the system, we draw agents and items that arrive. Every agent has a super simple decision. It just sees the expected waiting time given the queue length, decides whether to join or not. And under the stochastic process, we're going to get some distribution of queue length. And you can see that the queue lengths are actually centered around 25. Around like if you multiply by the waiting cost per item, you get that the waiting cost that this is centered around is actually in the sense the correct waiting cost. This is the p equals to a half. Okay, I guess we can't really see that. Yeah? But you don't really but most agents will not see a price, an implied price by the weighting cost that is actually exactly equal to a half. Some will see something that's closer, that's below 0.4. Some will see something that's above 0.6. And what that means is that if my value is 0.4, the optimal thing would be never to assign me. The offline optimal thing, if I didn't have the stochastics, would be that the agents with a value of 0.4 should not get assigned. But there is a good probability that the agents with a value of 0.4 will come at a state where, like, they randomly draw some state in which they arrive. It happens to be a state where the queue is abnormally short, and they actually do join the queue and do get assigned. We can think of the fluctuation of the queue length, the fluctuation in prices. Sometimes the price will be just too low, and then we assign agents with a value that's too low. And of course, there's the flip part of this, that the agent with a value of 0.6, this agent will come where the queue is abnormally long, and the price is just randomly too high, and then this agent does not get assigned. And then we get some misallocation. Sometimes we don't assign agents that should be assigned, and vice versa. So there's going to be some welfare loss from this. To better see the welfare loss, we can just draw the implied probability that an agent will get assigned. So on the horizontal axis here, I have the agent values distributed uniformly between 0 and 1. The black line gives the optimal assignment probability. Assign agents if they have a value above a half. If they have a value below a half, don't assign them. And the blue line is the implied assignment probability under the steady state distribution, where the prices will randomly vary. And you can see that those two areas correspond to misallocation of agents and lost value. Like, I'm going to get lower allocative efficiency from agents because some agents get assignment probability that's below 1, although it should be 1, and vice versa. Okay, so what we want to do in this talk is try to understand what is going to be this allocative efficiency loss for a much more general market. If I take a market, there's not just one item, there's many items, and I think of this stochastic price adaptation. I take this waiting list. Prices are going to be randomly evolving. Some agents will see prices that are wrong and will take the wrong items, or will get misallocated, or will not take any item, and there should be taken some item. And what we want to understand is what is going to be the allocative efficiency of the stochastic system.
Jacob, can I ask you something before you move on to
of course.
So, you know, taking the cue from the paper that was presented a couple of weeks ago by Piotr Wojak and his co-authors, you know, they could argue that what you call misallocation, it's actually, you know, welfare. So welfare weights put to, you know, people with lower valuations, right? So how does your work relate to theirs? You know, in the sense that in what you say about what you call welfare losses, they would say, you know, you can imagine that the designer or whoever creates these type of markets, they do have, you know, fairness considerations into account, and they actually want to allocate some of the goods to lower value agents. Does your model speak to that type of questions?
In this kind of environment that is specified, there's nothing good about this misallocation. If I wanted to give the item to agents of different values, I could, like, just choose random prices or just randomly give the item, right? So I think in their mechanism, they ask, when are prices the right thing? And in some environments, you have other considerations like budget constraint agents, where prices are not necessarily the right thing, and those will be true, kind of like, you know, I think in their kind of like specification that has extra desiderata for the planner. we just think of like whether prices work or whether they don't do their job. And of course, like the fact that the prices don't do their job as well as they should be in competitive equilibrium might be good in some kind of like in some settings, right? But like what we're interested in is like kind of understanding, are they going to do what we think that usually prices do and maximize allocative efficiency, or do we find that they do something different?
I see. So that's the end game of your so the end game of your paper is to say whether, you know, this mechanism where prices are discovered via queues creates you know, significant welfare losses or not.
Yeah, like if you think of prices as doing the job of guiding the allocation, maximizing allocative efficiency.
Okay.
And I want to think about this waiting list. Can I think of this waiting list as something that will be a parallel of competitive equilibrium, even though it fluctuates and there's like some noise there? And if you want to change prices from price mechanism to something else, probably there's a lot of things you want to consider. But like it's not like the competitive equilibrium is a perfect solution in any environment. But like what we're trying to understand is like what happens when you add fluctuations on top of a competitive equilibrium. And let's just take everything that's related to the competitive equilibrium given. Let's suppose that competitive equilibrium would have worked here. So if I could do the offline benchmark, that would be the right thing. That would be the best thing. And that's what I'm going to be assuming here. And I want to focus on one thing, which is the random fluctuation, and see how can I deal with that.
Okay.
Okay.
Okay. Thanks.
Okay. Yeah. Thank you. Yeah. So, okay. So that's a great lead. So our question is, we're going to have an economy where we're going to have fluctuating prices, price adaptation, some sort of total model that operates, prices will move around, and we're going to see what it does for allocative efficiency. Our main result is going to be that we can actually give a characterization of the allocative efficiency in pretty general environments and kind of identify one key statistic of this mechanism in the environment that actually gives us a bound on welfare, which is a step size. What will end up mattering is how much prices, expected waiting cost, how much they change with every adaptation. Every time that one agent comes and joins a queue, how much does that change the price? You can think of apartments arriving every 6 months, and then every time somebody joins the queue, it changes the price by 6 months, which is a really big change. Or you can think of apartments arriving every week, and maybe you still need to wait for 2 years, but every time somebody comes and joins the waiting list, it only changes the waiting time by 1 week. So that would be a small price, a small change. And our result will show that this is the right statistic to look at to understand how much allocation of efficiency loss you're going to have because of the fluctuations. So we're going to have a formal bound. I'm going to show you that the bound is tight. We're going to have an example showing you that the loss is exactly the bound. And we're also going to have conditions showing when you can expect the loss to be negligible, saying something about the structure of the problem, like what about the structure of the problem relates to the size of the loss. From a methodological perspective, I kind of think that we do something interesting relating the price discovery process here, trying to understand it. And from a technical perspective, we get a lot of tractability by recasting it as a stochastic gradient descent, as a sort of optimization algorithm. And I'll be clear later. I'll go into detail about what I mean by stochastic gradient descent, how this all works. But basically making this connection between the way that prices adapt under the waiting list and this optimization algorithm allows us to use a bunch of theory from that literature, duality theory and some Lyapunov function that gets us to this bound. And I can basically give you the entire proof in this talk once you kind of use those approaches. And last, if I'll have some time at the end, I'll try to talk a bit about price rigidity. So I'm by no means a macroeconomist, But one of the things that come out of this kind of like of this model is that it's bad to adapt your prices too quickly. So if you adapt the prices a lot every time that one agent comes, if you adapt them quickly, you're going to have a lot of loss from the fluctuations, which naturally will lead you to adapt slowly to changes in the economy. If you're unsure about whether things change or not, you may be responding more rigidly or more slowly. And kind of like, I'll say a couple of things there, how this model can kind of like pretty naturally generate a price rigidity behavior. Okay, so this is of course very kind of partial slide about related work, but a couple of things that I want to note here is one is that there's a lot of papers that came out recently. This is of course very partial little view about like dynamic allocations. A lot of those papers look at the one-dimensional case. Because in the one-dimensional case, you can write some Markov chain and calculate the stationary distribution and solve it in a tractable way. We're going to look at a multi-dimensional case, more than 2 items. Like you're not going to get a one-dimensional Markov chain here. So we're not going to be able to calculate the steady state of the system. That's not going to be tractable for us. And that's why we have to adopt those different approaches. Yeah? And this has been a limiting factor for a lot of this work in the literature, including some of the, I was stuck with those hurdles in some previous work too. Another comment is that there's a lot of papers about price discovery or stochastic random descent algorithms and kind of like learning prices. One big difference between our work and all of this work is that they generally think that prices are learned and at some point you converge and that's it, you're done. And in our model, we're going to think of learning and price adaptation that never stops. Like the waiting list continuously adapts, and you can think of this as an analogy or fable for a firm that learns prices and is not sure whether demand changed or not. So in some sense, you get like your demand from January, you get something back from February and it's different. You don't know whether something changed in the market or whether like this is just noise, right? Like there's going to be some tension there. And we want to think of the waiting list as kind of like a price discovery that's kind of ongoing and never converges. And there's some work in IO about the price of fluctuations, a lot of work in the 70s and some more recent work. Yeah.
So Jacob.
Yes. Hi, Simon. Yeah.
Hi, good to see you. Just a quick question on the interpretation of price discovery, or I mean, I think you alluded to it a little bit that there's not going to be any convergence, but say, if you look at the static setting, when all the agents are present, we can still ask, you know, what on the incentive compatibility, etc. How can we set the appropriate market clearing prices, right? Mm-hmm. So there, for a finite number, whatever the realizations, this market clearing price that you need to discover to implement efficiency is well defined, and it will vary depending on the realizations of types, right? Mm-hmm. Whereas in a dynamic setting, it's not quite clear what prices you actually want to discover, right? Do you want to set prices that give the right incentives to the agents who arrive, or do you set prices once the agent has arrived and accounting for his type or willingness to pay?
So can I hold on this question and come back to this?
Sure.
So I actually wanna I think it will be good to come back to this after I present the result and some connection to the offline problem. We have some connections between our problem and static market, and maybe after I talk about this, discuss.
Okay.
Yeah. Okay. Okay. So give our model and kind of like do the straightforward kind of like model here. We have item arriving according to a Poisson process. The arrival rate in total of all items is normalized to be 1. This is just a normalization of time units. There are finitely many types of items, denoted 1 to j. And with probability mu j, the arriving item is of type j. And you can think of mu j also as the arrival intensity, arrival rate of item j. Agents also arrive according to a Poisson process. The total arrival rate of agents is lambda. When an agent arrives, we randomly draw the agent's type from some distribution f. And types, agent types can be continuous, finite, whatever, like any distribution of agent valuations and types, fine. An agent will have a quasi-linear utility. We're trying to parallel the competitive equilibrium in which like the allocative efficiency maximization will be the thing that the planner would like to do. The type theta agent will have value v theta j for item j. All agents have the same cost of weighting CW. You can think of this weighting cost as being linear throughout the talk, but if it's concave or convex, that's fine too. And the only technical assumption that we really need is like that those values, like the weighting cost is smooth, and that the value is bounded. So there's a maximal value for items. Okay. Given some assignment eta that just specifies which item or being unassigned, which item is given to which agent and which agents are living unassigned. Unassigned agents leave with a value of 0. And given some allocation, we just like calculate what is the average value of assigned items. That's what this expression gives. Just take time, limit of time to infinity. We use t to index arrivals, both agents and items. So CT is just an indicator that the tth arrival is an arrival of an agent. And we just calculate all the value assigned to items, but every time that an agent arrives at time t, this indicator is going to be equal to 1. And then we're going to say how much value did we generate by assigning agent theta t item of type eta t. And then we sum over all agents, take time to infinity, and I took lim infinity here to make sure that it exists, but like we're going to have an ergodic system. This thing will exist for everything that we care about. And this will give us the allocative efficiency. Okay? And we're going to denote the optimal allocative efficiency as the expected value of what you get if you just take the optimal allocation and you take expectation over the potential arrival processes, all the potential arrival processes. Okay. The mechanism that we'll be analyzing is, again, like what I said in the beginning, motivated by what happens in New York public housing. It's a very simplified version of this very, I think, straightforward mechanism. Whenever an agent arrives, they can join a specific queue for each one of the items. So for each item J, there's a queue for that item. The agent that arrives sees how many agents are waiting for each one of the queues. So he sees the implied price, expected waiting cost for each one of the items. And he can choose one of the queues to join or just like leave unassigned. Once the agent chooses, that's it. There's a single choice. Again, to make it as simple and as parallel to competitive equilibrium, the agent will make one choice. There's no reneging, no switching queues. We don't allow any of those things. Yeah? So the agent basically just says, I only need to care about what's expected waiting cost for each one of the items, because when I join the queue, that's it. There's no more decisions to make. Okay? I know what's my expected utility once I make my choice. So when an agent arrives, the agent value is going to be private information. The agent will make a choice that we denote by A theta Q, Q being the current state of the system. It's a vector specifying the length of each one of the Qs, one Q for each item. And the agent, just like in competitive equilibrium, maximizes the value of the item minus the implied price. We can think of this expression as being the price of item J. If you want to get item J, you need to join the Q for item J. We're going to weight the expected waiting cost for item J given the current state of the system. And since we think about this as price, it will be also useful to just denote it as prices. So we're going to denote Pj of Q, the state-dependent prices, given that the system is in state Q. So if we have this many agents if we have Qj agents that are already waiting for item J, I can calculate what is my expected wait. If my waiting costs are linear, it's just going to be 1 over the arrival rate of item J. How long do I have to wait for one arrival, times C times 1 plus Qj, which is the number of agents that I'll have to wait behind. Okay. Okay, so model clear? Okay. A couple of other things that we want to denote and use later. One is that WWL, this notation is the welfare, is the allocative efficiency, the average value of assigned items under the waiting list mechanism. Suppose we take this mechanism, we run it, every agent chooses the queue that maximizes their own private utility. We take expectation over the arrival process. This is going to be the allocative efficiency under the waiting mechanism. And one expression that's going to be important for us, as I said before, the step size delta is going to be the maximal difference due to one extra agent on the waiting list, on a queue. So suppose one agent came and joined Qj. That means that now I have to pay a price Pj of Q instead of Pj of Q minus 1. One more agent joined the queue. So it increased the implied price for getting item J, maximizing over all possible items and over all possible queue size, where there's going to be some maximal size of the queue because agents have bounded valuations. So after some length of the queue, the price is too high. They're not going to wait further. There's going to be some maximal size of the queue. So, taking the maximum of all this, we get that this is just going to be the global bound on how much can the price change from one arrival. And if you think of linear waiting costs, this bound is actually pretty simple. Each extra agent on a queue just means that you have to wait for one more arrival. So this is just the cost of one arrival of the most rare items, right? If all items arrive at the same rate, like this is just 1 over mu for all the items. Okay, so now one natural way of just analyzing this question of what is the allocative efficiency would be to just say we have some stochastic system here. It's going to be a stochastic process. The state is going to be the current state of the queues. Given the state, we're going to have prices. Given the prices, there are going to be some probabilities that an agent will join one queue versus another. And if an agent arrives and joins Qj, we just move to a state in which Qj now has one extra agent waiting on it. If we were some state Qt and item J arrived, now we cleared one agent from Qj. So now we move to a new state where one less agent is on Qj. And overall, we have all those random transition, and we have some set of states and some Markovian process over them. and we're gonna have some stationary distribution. And as I said, like we would like to just calculate the stationary distribution. If we calculate the stationary distribution, I could do the same exercise as I did with the one item at the beginning and just calculate what is the allocative efficiency loss from that. But when we have strictly more than 2 items, the stationary distribution is not tractable. So there are some operations papers that try to deal with that, and some even have computational complexity hardness results for calculating the space. So we can't go down this avenue, and we're gonna have to come up with a different way of evaluating the allocative efficiency loss. And the way we do this is we can give you a bound on what is the allocative efficiency loss. So let me jump to the main result. And then after I state the main result, I'll tell you a bit about how we got to the main result and try to make sense of it. So what we find is that the step size, this delta, the maximal change in the prices due to one arrival is actually also the maximal allocative efficiency loss due to the fluctuations. So if we take the welfare under the waiting list, it's always at least as big as doing the optimal assignment, the maximize allocative efficiency, but incurring a loss equal to this delta, to the step size. And if waiting costs are linear, you can think of this as allocating all the items optimally, but making each agent wait for one arrival. So the allocative efficiency loss is at most the loss for making each agent wait one extra arrival. Okay. So to put a bit more sense of this, like if you think that apartments arrive every 6 months, the price of an apartment should be something like 2 years, but every time an agent joins or leaves the queue, we change the price by 6 months, or 25% of the price. That's going to cause a lot of fluctuations and a lot of loss, a loss of order of making everybody wait another 6 months for the apartment. But if apartments arrive and go, arrive every week, then the step size is going to be 1 week and the loss is going to be very small. Okay. Okay, so let me try to tell you how we prove this result, and by that, try to make sense how we made, at least for us, made a bit more sense of the problem by relating it to two other problems. The first is the offline problem, or the static allocation. I started in the one item case trying to say what will happen if we could freeze all the agents and just unfreeze them and do a big batch allocation. So this problem here is exactly that. So suppose I take the expected amount of agents that will arrive per unit time, expected amount of each kind of item that arrive per unit time, and I want to do the static offline allocation between them to create the maximal allocative efficiency. So my decision variables will be just to decide how much of item J will each agent theta will receive. That will be the shares of agent of type theta for each theta and J. That will be my objective, to maximize the allocative efficiency, the value of assigned items given the shares of each item that I assign to each type of agents. So I sum of all agents, sum of all the types of items, integrate over the types of agents with the density of agents, and this is what I get as total allocative efficiency. And this scaling number just is scaling by the amount of agents that I have. This constraint just asks that the shares are well defined. I don't give agent theta more than 100% of items, and other shares are non-negative. And the last constraint is just the resource constraint. I cannot allocate more of item J than item J is actually arriving. Well, everything here is taken in expectation. So like I take the expected amount of item J to arrive, the expected amount of all the agents arrive. And you can think of this would be the constraint if I just take a long interval of time and just like accumulate all the agents and items in this interval and then do the static allocation. Because then I will get something close to the expected. So that would be the static value, and the proposition that we get is that the optimal value in the dynamic allocation is actually exactly the same as the optimal value in the static assignment. So it's not that the static and the dynamic are exactly the same. There's a bit of wedges between them, but you can think of almost, there's a bit of an asterisk there, but let me avoid the asterisk and just say that suppose we could just run the waiting list and lie to agents and just tell them that there's some static prices that are always posted. If all agents see the same prices from the static allocation, they'll all make the same decision as in the static problem, and we'll all get the same value of items as in the static problem. And therefore, we can get the same allocative efficiency as in the static problem, even in the dynamic market. So there is kind of like some sort of connection between prices that you want to set in the dynamic market and prices in discrete. And another way to kind of like state this that would be, in addition, useful for a step in a couple of slides, is that we can think of the dual of the previous problem. So in the previous problem is just a linear program. We can take the dual of it. It's an infinite dimensional linear program, but we can take the dual of this infinite dimensional linear program and write this as this dual, where the dual function takes the dual variables for the previous one, the prices, okay, and those are like the Lagrange multipliers on the resource constraint. And for each one of those, we get some expression here that's it's pretty standard. It's not ours. It's a pretty standard duality formulation for this. And the question of optimizing welfare can also be stated as finding the prices that minimize this objective function, this dual objective. Yeah, and Simon, maybe now, and I don't know if now is a good time to get back to your question, but I was hoping that maybe this helps make a connection between the static and the dynamic problem.
Yeah, it's a good way of keeping the audience tuned in, right?
Sorry, not meaning to put you on the spot. It's just like this is the point that I thought would be useful to get.
Yeah, so you know, in the static model, the way you formulate it, I think it corresponds to a setup where you have a continuum of agents. So there's a single market clearing price, but there's an intermediate step one where you have, or the intermediate version of the static model where you have finitely many agents, and so the market clearing prices are stochastic.
Yeah.
And so in your, well, I'm still not quite clear what kind of prices you would want to discover, or what's the purpose of the prices you're after, or what would be, how would you define efficient prices in your setting?
So
what we got both the dynamics, so there's uncertainty about the future arrival of agents, so there's a speculative element to that, yeah.
So what we will have that, partly it's because we look at allocative efficiency, which means that it's okay for us if agents wait. If we tell agents, those are the prices, and they're not, if we take this, we take P star, if we take a P star that's an optimal for this dual objective, and we just post it, it means that we always get agents to choose the items that will maximize overall allocative efficiency. But it may mean that they will wait longer or less at a given moment, at a given state. And we're not adjusting the prices to be state dependent to adjust for that. I guess if you have a market which is randomly drawn, you kind of like, you'll have some desiderata that says, I don't want to just keep drawing more and more of the market and have the agents wait until I have convergence to like the big market. I want to assign agents now with the price that clears the market now.
Okay, so an important aspect seems to be that the prices are not state dependent. Is that?
So to maximize our objective, you would want the prices not to be state dependent. The weighting cost of agents, the private weighting cost of agents will be state dependent, and our objective does not account for that. We don't we amortize that over time in a way that the agents may not want to, or that other objective may not want to.
I see. So it's a little bit more like a static setting in that sense. You don't account for these trade-offs of weighting versus allo.
Yeah, I guess. Yeah. So, like in operations, they often think of inventory problems, where you want to change your pricing as a function of your inventory. Here we like the planner does not have such constraints. Like, you know that like all the items will eventually arrive, and to maximize allocative efficiency, you should actually not look at your current inventory. That's not going to be the relevant metric in our model. For other reasons, it will. Let me maybe move on, and maybe we can talk after more about this. Okay, so the connection to this offline problem and its dual is actually really helpful in another way, because it helps me draw a connection now between what the waiting list does in its price adaptation and the stochastic gradient descent algorithm I'll describe in a minute. Okay? So as we said, all the transitions of the prices are going to be stochastic. If an item arrives, some queue will become shorter and the price of that item will go down. If an agent arrives, depending on their type, they will choose some object, so there's some random choice of which object they choose, and the price of that object goes up. Okay? And there's going to be some there's going to be some price that's going to be optimal for the dual, for the offline dual. And we can think of something that's kind of like randomly bounces around over some set of prices. And we may want to think of how close it is actually to this P star, to this price that would clear the market perfectly if we just kept it constant at all times. And one kind of like big observation that was very helpful for us is that the price adjustments are all going to be random, but the expected adjustment to prices makes a lot of sense. Because if I look at the expected change in the price or the length of a queue, there's going to be two items here. One of which is the probability that an agent arrives. This is, if I draw the next arrival, with this probability, it's going to be an agent. With this probability, it's going to be an item. If it's an agent, the agent will choose some item. And that's essentially the probability that the agent chooses item J. With this probability, I'm going to increase the size of Qj. With this probability, it's an item that arrives. And with probability mu J, the item is of type J, and the price of item J will go down. Those two things end up being exactly the derivatives of this dual objective. Okay? So the dual objective is exactly about prices and demand in the same way that what I get the expected change in price is exactly the probability shares of how likely an agent to demand an item given this price. And this means that the connection to Tatanomar, to the price adaptation in the beginning, is not just like it kind of seems similar. It's actually really a very precise form of Tatanomar. Every time we adjust the price based on a single agent, but if we were to adjust the price not based on a single agent, but based on a representative sample of agents, if we took many samples of agents making demand given the current prices, and then take the expected adjustment from this, we'll exactly increase prices according to how much an item is over demanded. And this will be exactly a gradient descent algorithm. Like we take the dual objective. The dual objective tells us, in a sense, how far away are we from the optimal prices. That has to do with how over demanded certain items are. And if we take a representative sample and take a step will be exactly a gradient descent step that tries to improve upon this objective. Now, what we get is a stochastic gradient descent. A stochastic gradient descent is just a variant of gradient descent where you don't take a step in the direction of the gradient at each time. You just take a random move that in expectation is the same as a gradient. This has become very popular for machine learning techniques where it's very hard to calculate your objective, your entire objective. So what you do, you take one sample from the distribution. You take one sample, you calculate the value based on this one sample, you update and take the subgradient, a step in the subgradient. In expectation, you took the move in the right direction, and it will take you a while to do many draws because you're doing this randomly and you're kind of randomly working, but it works. It's a way that makes it feasible to actually take this gradient descent optimization and apply it to very complex neural nets. One big difference between what we get and the neural nets thing is that if you want to do a gradient descent or stochastic gradient descent and have it converge, the step size must go to 0. The step size must become smaller as you become closer to the optimum. In our case, we get something that looks a lot like gradient descent, but the step size is constant. And the step size is not even something that's set. It depends on the parameters of the environment. It's whether apartments arrive every week or every 6 months. If apartments are arriving every 6 months, the step size is going to be big. If the apartments arrive every week, your step size is going to be small. So it's just a function of the parameters of the system. It's not even a design choice in this environment. So now that kind of gives us some way of looking at the problem that now kind of allows us to take some techniques from this literature that analyze stochastic gradient descent algorithms. So now we basically ask, if we have a stochastic gradient descent algorithm that does this price adaptation, but based on samples, sampling not a representative over demand of all agents, but just whether the next agent will give us some sample from demand. We know that we're going to get something that goes towards the objective, but never actually converges to objective. It will bounce around the objective. So we have some intuition that it should do relatively well, but not perfectly. And we can use techniques from this literature that analyze stochastic gradient descent, all the computer scientists that studies those algorithms, and use those to get it bound. So let me introduce a bit more notation. You don't really need to remember all those letters, but one thing that's very useful from this literature is to define the Lyapunov function, which you can think of as a potential function. So think of a ball that's bouncing around the heels, and sometimes the ball bounces against some wall or something, causes damage. And maybe it's kind of messy to kind of keep track of every property of the ball, but I can think of its elevation, its height as some sort of potential that goes up and down. Maybe the ball climbed a hill and lost some speed, but it's up, so there's some potential energy, and it kind of smoothes over things to remember that the ball has potential energy. So we're going to define the Lyapunov function that's going to be something like potential energy, like the height of a rolling ball. Okay? And this DL is just some expression that has to do with states and the Lyapunov function. And some extra notation to denote the arrival process. Anyway, but like, let me kind of just talk over the expressions. What I have here, this is the expected value that I'm going to get from the next arrival, conditional on the state being Q. Okay, so suppose the Qs are in a certain configuration. I know how many agents are on each Q. Disk C is an indicator for whether the next arrival is an agent or an item. I'm only going to count the value that I get when an agent arrival gets assigned. So I only care about agents arriving. And the value here is the value that the arriving agent theta assigns to the item that they choose, given the state, given the current state QT. Okay. Okay. What we have on the right is the decomposition of this to three things. One is the dual objective. This is related to the static offline problem. It basically takes the prices given the current state as its input. A second thing is a change in potential. And a third thing is some expression that will just be the loss. Okay? And now, And now one useful thing is that I can change this dual objective. This is a bunch of algebra, like you can just do a bunch of algebra and show that you can write things this way. You can bound the dual objective by the optimal value from below. This is weak duality. And now we have something that relates the value that we're getting from the next arrival to something that has this change in potential and this loss. And this loss can be uniformly bounded by delta over 2, by the step size over 2. And what this means is that no matter what this Q is, the current state is, once I capture some of the differences by loss in potential, I basically smooth things out that like I get a uniform bound on what is going to be the loss that I get from the next arrival. How much allocative efficiency am I going to generate? How much value am I going to generate from the next arrival relative to the maximal possible? Well, some of this is going to be absorbed in a change in potential, and I'm going to get some loss that's at most delta over 2, regardless of what the state is. And now the last thing that I need to do is kind of like just look at this change in potential and bound this. Okay? Once I do this, I know that this optimal value is the same. This is the same as this W, the optimal W. Okay? And there's this constant that will go away. The only thing that's left to do is to deal with this change in potential. And this change in potential will just go away once I kind of look at telescopic sums. Because if I look at many, many rivals one after the other, I will, let's think of like, once I get to the optimal prices, I will start going in cycles, drifting away to far away places, and then going back to the same places back. And this is where it helps to think of elevation, because it's like the ball gains elevation and then loses elevation, gains elevation, loses elevation. At the end of the day, everything cancels out. And all these terms will just like turn out to be like insignificant once I take a sum over many, many arrivals. At the beginning, I may have some constant at the beginning, but as I think of time going to infinity, eventually over time, I'm going to have some transient thing from this, and then it's going to go away. Okay? So overall, I get that this will give me the loss, and after factoring a couple of things, this ends up to be a loss of delta per agent. Okay. A couple of other things, we can say something about like the the tightness of the loss. So we have an example. Do I have until when do I go?
Until 15. So there's another 11 minutes, but plus or minus something.
Yeah. Okay, so let me just go quickly through a couple of other results. Okay, so one is like we have an example where the bound is tight. So like the loss is up to some small rounding, really this delta, and it's actually a very simple example. You just have, you can have as many items as you want. The important thing is that there's agents that like only one item, and the arrival rate of the agents that like an item is exactly equal to the arrival rate of that item. And then like we can just calculate what happens under this economy. It's going to be some prices are going to follow some random walk. And every so often prices are going to just hit some boundary when some agent will say the price is too high and will not take any item, leave unassigned instead of taking the item. The likelihood of that happening is proportional to the size of the queue. The size of a queue is proportional to 1 over the size of the queue. The size of the queue is proportional to 1 over the step size. So overall, you get that the loss is the step size, ignoring some constant to cancel out. And then we also have some examples showing when do you expect the loss to be small. One thing that's pretty non-generic about the previous example is that there's a big set of prices that will be market clearing prices in the static equivalent of the economy. Like if you have exactly demand equal to supply, the amount of agents that want an item is exactly equal to the amount of the arrival rate of the agent, the item, the arrival rate of agents that want an item is exactly equal to the arrival rate of that item. Then you get that there's a lot of market clearing prices. This is not generic. And we get that if you have finitely many agents, and the generic case in which prices are unique, then we get a much tighter bound for welfare loss. The allocative efficiency loss. The allocative efficiency loss is going to be exponentially small in the step size. And the intuition is that if you have this like finitely many agents and prices are unique, it must be that the agents have a strict preferences to take the items that they're supposed to take under equilibrium. Which means that there's a box of prices. Well, as long as we stay within the box, nobody will ever take an item they're not supposed to. So I have some neighborhood of prices. As long as I stay within this neighborhood, I'm good. And the next thing is like whenever I'm in this neighborhood, I'm actually gonna have a biased random walk. The demand is such that I have a very a much stronger tendency to go back towards the right prices rather than to pop out. There's going to have to be a bunch of sequence of very random events to make me go out, because like once I shifted away a bit, like I would like to correct the prices. So put together, you get that it's very unlikely to have allocative efficiency loss, and that like the loss is in some sense related to the properties of the dual. If the dual is pointy, if the dual is sharp, then you expect to have low allocative efficiency loss. If the dual objective is flat and you have many optimal prices, then you expect to see more allocative efficiency loss. Okay. So let me take like maybe 3 minutes to just make a comment about price discovery, and then I'll conclude. So now I'm kind of like trying to think of this as kind of like as a fable. So this is a very concrete model of price discovery when we know exactly how the waiting list adjusts prices. So I know exactly the procedure that the waiting list does. I know how exactly to adjust prices, but in some sense, you can think of like firms in general trying to discover prices. This graph on the right is from like a slide that I had when I taught business analytics to MBAs and master students, and told them that it's like, here are what firms were pricing. Look, those numbers are all over the place. They don't know what they're doing. If you learn this class of business analytics, you can do better pricing. Okay? And of course, our pricing algorithms are complex and they do different things, but in some sense, you can think of this stochastic gradient descent as a simple heuristic, or like some kind of like story or starting point to try to think about how firms adjust prices. And it gives some tension that I think is present in a lot of pricing decisions. When you get new information, when you get more new arrival, you'll adjust it according to some step size, whether you make a big or smaller adjustment. If you make smaller adjustment, it means that you will have less fluctuations and less of the loss that this paper focused on. Like if you were to reach steady state in the long term, you will have less fluctuations if your step size is small. On the other hand, what the model ignored and abstracted away from is that you might want to have a big step size. Like if you're trying to get to a price of 2 years from some public housing project, and each person that joins just adds 1 week to the waiting cost, it will take a long time until you reach the correct prices. If the queue is starting empty, there's going to be some transient time, transient but maybe long, that you maybe should care about, that the price discovery is going to be low. It's going to take a time while before you actually get to prices that are ballpark correct. So if you have some finite horizon, or the environment keeps changing and you don't really know whether the environment changed or not, you have to make a trade-off between those two things. If you make too many adjustments, you're going to have too many fluctuations and loss for that. If you have too little adjustment, your prices will be stagnant, and maybe they're going to be outdated. And if the world does change, you're not going to be responding in time. Balancing those two things, you're probably going to choose some intermediate value of this step size delta. And if you think about it in terms of price rigidity, that gives you an explanation for why a firm may not want to adjust prices as quickly as you might expect. They basically are choosing a smaller step size because they're not sure that the world actually changed. They may think that there may be some fluctuation and want to protect themselves from just fluctuating the prices and causing this efficiency loss or some other loss if they curve a profit or something else. Yeah. Okay. Of course, I'm not a macroeconomist, but that's one reason why you want to adjust things slowly. Okay, so let me just conclude here. So we think of the allocative efficiency in waiting list, whether the way that waiting list allocates will correspond to the static prices that you can think about if we just had the expected amount of agents and items all at the same time. We find that like you can think about stochastic price adaptation using stochastic gradient descent, which allows us to give bound. And we find that the stochastic price adaptation do cause a loss, an efficiency loss, but the simple adaptation process actually does relatively well. And the loss, to understand the loss, we need to understand the step size. How much do the prices change with each cycle, with each adaptation? So that's it. Thank you very much.
Thank you so much, Jacob. Thank you. I'll stop the recording now.